I want to take a minute and look at how we solve problems with speed and velocity. Let's recall our equations that we know to relate these different variables. The first one we typically see is one to relate speed. And speed, which typically is in units like miles per hour, meters per second, well, the units tell you what its equation needs to be. It needs to be a distance unit over a time unit. Right? And with a little algebra, we typically will see that rearranged, if you multiply both sides by t, you would have distance is equal to speed times time. Or we can solve for t, and time is equal to distance over speed. They're all the same equation, just algebraically manipulated. Now, speed and distance are what we call scalar quantities. They don't have a direction. You don't get pulled over for going west versus going east, right? Unless you're driving on the wrong side of the road, right? You go over for how fast, right? And when we run around a track, we don't care that we ended the same spot. We care how far we went, right? So the distance is just the total path that we travel. But if we do care about direction, we now have these quantities of displacement and velocity, right? So we typically see another form of this equation where we have velocity, and velocity is what we call displacement over time. And I can rearrange that and have displacement is velocity times time, and time would just be displacement over velocity, right? So you have the same three equations, except we've now replaced the scalar quantity of speed with what we call a vector quantity. All right, so this is a scalar quantity. All right, so scalar are like speed and direction and distance. Right? They have no direction component. They're just an amount. Call that a magnitude. However, velocity is what we call a vector. Velocity and displacement are vector quantities. They have magnitude and direction. And so we can say I'm going 20 meters per second, and that would be what we call a speed. However, I could say 20 meters per second to the east, and now I have a velocity. Now notice the number part remains the same, right? And that's the part you're going to be calculating with, all right? But we do have a direction component, right? And I could say that I went 10 meters, and we would say that that's a distance. Let's slide this down here. That would be some distance that I might have walked, right? Or I can say I went 10 meters to the east. And now I've specified a displacement. It has a direction to it. If I start somewhere and I go east 10 meters, that would be different than traveling west 10 meters. They would both be the same distance though, right? And so this distinction is important when we start getting into physics problems. And typically, we can solve every problem with these equations and get the answers as the speed and direction, which is why I typically don't use these equations very much, because they're the same as these equations, but with the extra information of the direction as well. Right? So I'd encourage you to stick with velocity and displacement moving forward, only because it allows you to have extra information that you can use to answer the question, or maybe you don't need. All right? But I want to take this a step further and start looking at how we actually solve some problems with it. All right, I'll make a little bit more space. We're going to get to this example problem. So if I take my displacement equation, delta x is equal to velocity times time, well, this actually can be stretched out to give us even more information, right? Sometimes I start at a position and I finish at a position. Well, delta x is just a change in position. And so that equation becomes that. Or I can rearrange and find that where I'm located later, my final position is my velocity times time plus where I started, right? So this is my one equation that we typically use to solve problems, right? And this is an equation for a line on a position versus time graph, right? So this will show linear motion. So this is going to collect all of our information it can use for any problem. Now, most problems, they might tell you how far you went. Well, what is your initial position then, right? The initial position, x initial, right? We call this our initial position, right? Is typically, or can often be, 0. We decide where 0 is if they don't tell you, right? So if we travel 10 meters, a 10-meter distance, we can say that x initial is equal to 0 meters and x final is then 10 meters, right? And if we do that, then delta x just becomes 10. And this equation we can just use as x equals to v times t, right? It simplifies, and that looks just like those other equations we had up here. So delta x can be confusing because oftentimes we don't care about our initial position because we can decide to call it 0, right? So we effectively move everything down to this version here, right? And so if we have this equation up here, right, I like to tell you to set up a t, v, x table. If they just tell us how far, then we can call the initial position 0, and x is my distance. Or they might tell you there is an initial position, and we finish somewhere else, and we can treat those two values, and we can solve for all of those things, right? So this is a good way to organize your work for any problem where an object's moving in one dimension. All right, so let's look at a quick example and answer some questions related to this. All right, so this is a typical example you might see with one-dimensional motion. John walks 10 meters east for 4 seconds, then turns and walks 20 meters south for the next 6, pauses for 5 seconds, then turns back west and walks 3 meters in the last 2 seconds. Well, let's draw a picture, right? So what's challenging about this is there's 4 different motions. Each motion is its own problem. It's its own one-dimensional problem, right? So let's look at where he starts. Let's start him here. Right? This is his starting position. He's going to walk east for 4 seconds, a distance of 10 meters, and he's going to be right here. And so for section, we're going to call this section 1, and we can set up a table here. We have a time for 1, we have a velocity for 1, and we have a position for 1. Now, because it's a distance he travels, I'm going to say, we can say the displacement, or delta x, is our 10 meters. Our velocity we don't know, but we know our time is 4 seconds, right? Do you see how we set up that same table? But what we've done is basically said x initial is 0, and x final is 10, which gives us a displacement of 10, right? And because we only have 3 things, we can solve for v, right? And velocity is displacement over time, right? So again, velocity is always going to be displacement over time. And so I can do 10 divided by 4, right? And I get 5 halves, or 2.5. This can be calculated as 2.5 meters per second, right? And we know that now, right? But next he walks 20 meters to the south. So I'm going to draw another dotted line. And that would be 10 meters. I'm going to try to draw it so it's the same scale. So I'm going to draw it even longer. All right, that's section 2. Section 2 has its own time, its own velocity, and its own displacement. And they tell me he walks 20 meters at some speed for 6 seconds. Then we sit right here and we sit there for 3, and we do that for a time of 5 seconds. And during that time, we're not traveling anywhere, and we are not changing our position. All right, so we actually know all 3. And then the last thing, we walk west 3 meters, which is going to be right about to here, and that's where I'm finishing my trip, and we'll call this section 4. And you can have a time for section 4, a velocity for 4, and a displacement for 4, right? And so technically we could say he's displaced left. For these, we're just going to call this a distance. And it looks like it was 2 seconds at some velocity for 3 meters. So I have this big picture set up here for the full trip, right? And it's 4 different parts that are kind of all strung together, one after another, right? And so we can actually fill in information here, right? If I take displacement over time, 20 divided by 6 gives me a value, right? I think it's 3 2/3, 20 over 6, 3 1/3. So 3.3 meters per second if I needed that. And 3 divided by 2 is 1.5 meters per second. So again, I've actually filled out, I know everything about my motion here. Well, so what's my average speed? Some people would take all 4 of those speeds, 2.5, 3.3, 0, 1.5, add them all up and divide by 4, right? Which is taking an average of 4 speeds. However, it doesn't account for the fact that they're happening for different times, and I think that's what's confusing, right? So what we need to lean on is our definition of average speed. Average speed is always our total distance over the total time it takes, right? So in this case, it's going to be the displacement from 1 plus the displacement of 2 plus the displacement of 3 and the displacement of 4. That would be how I would add them all up, right? And then my time of 1 plus time of 2 plus time of 3 plus time of 4, right? And when I plug in my values, I get 10 meters plus 20 meters plus 0 meters plus 3 meters. And in the denominator, my time becomes 4 seconds plus 6 seconds plus 5 seconds plus 2 seconds, right? So my average speed is 33 meters in a total time of 17 seconds. And if I pull out my calculator, I can evaluate that because it's confusing to leave it as a fraction. And we're going to get a decimal value of 1.94 meters per second. That's my average speed. But what if I ask for the average velocity? Well, we have to understand the difference in the definition. A velocity is a displacement over time. The total displacement over time. Total time. The displacement is actually the straight line path from point A to point B. This is our total displacement. And hopefully you see a little bit of geometry in here. Hopefully you see that we actually have a triangle right in here. And the length of that triangle, well, look at, I go 10 east and then 3 west. This should be 7 meters and down 20 meters. And I can use that triangle and do some trig. So this is a right triangle. And what we know about right triangles is that if we know two sides of that triangle, I can always calculate the third. And we use something that we call Pythagorean Theorem, right? This is 7 meters. This is 20 meters. And this is what I'm trying to find. And the two legs of our triangle, this is a right angle. There's A, there's B, and there's C. And Pythagorean Theorem says that A squared plus B squared is equal to C squared. And we have A, so 7 squared, plus 20 squared is going to be equal to whatever C squared is. Right? So if I pull out my calculator, on the left side, 7 squared plus 20 squared is going to be a big number. 449 is equal to C squared. And to solve for C, we just take the square root. The square root of both sides, or the second square root of the answer, gives me what C should be, 21.2 if I round it. So C, the length would be 21.2 meters. And so my displacement, delta x total, for the whole problem is 21.2 meters, right? And the direction is kind of like southeast, right? If I was going to describe the direction, right? But I want my average velocity. Well, my total time is still the same 17 seconds. And so my average velocity is going to be delta x total from start to finish over the time total. And that's going to be 21.2 meters over 17 seconds. And look at how my units work out. All right. And if I take that divided by 17 seconds, I get 1.25 meters per second as an average velocity. Now notice, that's actually slower than it would be if I took the full path. And that kind of makes sense, right? To get from start to finish in 17 seconds, I would not need to go as fast because I'm taking a straight line path. So that actually makes some sense. All right, so this is how we find average velocity, all right, and differentiate it from average speed. Remember, velocity is total displacement, so it's a straight line path. It's what they say as a crow flies, a direct line path. Okay, so we typically, when we do these problems, if we're changing direction, we would look at using Pythagorean theorem. I could, in some problems, sometimes the guy or the character will move to the right some distance and then return some other distance, right? And you would have some x initial and some x final. And the displacement would just be that distance from beginning to end. And the total distance would be the whole path. You'd have to add those two together, right? So that's how we would do it as a one-dimensional problem. There would be no triangle there, no need for a Pythagorean theorem, right? But it's the same idea. Now, the last thing I want to mention is this idea of instantaneous speed, right? At any given point, the speed of this guy is changing, right? These individual velocities, V1, V2, V3, V4, would be what we call the instantaneous speeds. And it turns out instantaneous speed and instantaneous velocities are the same number, right? They're the same, except velocity just has a direction, right? And so that's how we differentiate between instantaneous and average. Okay, so anytime you get these average ones, we got to stick with these two equations, right? Average velocity is always the total distance or total displacement over total time. And average speed is always the total distance over the total time, right? So that's how we're going to kind of set up some of these problems. But that equation will help you go. It's really important to draw a picture to identify what we have in the problem and to be able to organize our work. So hopefully this long video kind of gives you some direction for how to set things up. This particular problem is a two-dimensional problem because it goes east and south. A lot of problems are just moving left or right, in which case it's a lot easier just to set up your one table like this, plug in where you start, where you finish, and figure out the time or the velocity or whatever the missing piece is. But guys tend to have issues when we start changing directions here. If you get into physics classes later in your career, we can actually figure out from this information exactly what angle he has to go. And that's really when we get into a displacement. I said southeast. but there's actually a specific angle that he would have to go to get from point A to point B. And that's really how we would describe the direction of a displacement. We call that a displacement vector. But that's beyond the scope of what we're going to cover here. Hopefully this helped for you.